So modern AI assistants,
Yeah.
they're brilliant, right? I mean, they're incredible reasoning engines, but, and this is a big but, they have this massive immediate constraint.
Right.
They're only as powerful as the data and tools they can actually access.
Exactly. I mean, if your proprietary financial data lives in some private database or the tool you need is a locked-down internal enterprise API, the AI needs a way in, a secure, standard way to plug in and use it.
And that's the core pain point, isn't it?
Oh, absolutely. For years, every single organization building a serious LLM application had to write these custom one-off integrations for every single system.
A total nightmare.
It was. Anyone who spent 2023 writing bespoke Python wrappers for 5 different internal tools knows exactly the inefficient, non-standardized mess this creates.
Okay, so let's unpack this. We're diving into the solution proposed by Anthropic, the Model Context Protocol, or MCP.
Yeah.
This is an open standard introduced specifically to solve this exact bridge problem. And to steal the analogy from their documentation, which I love, you should think of MCP as a universal AI USB port.
It's a perfect analogy, actually.
Isn't it? It's a standard socket that lets you plug your reasoning AI into any data source, any service, and you just know that the connection is going to work predictably.
And the goal here is uniformity, its efficiency, and this is critical control. Instead of every company reinventing the integration wheel, we now have a common client-server architecture.
Right.
So our mission today is a deep dive into the anatomy of that server, the MCP server itself, to understand the 5 core components that handle all the data retrieval in action, freeing up the AI model to do what it does best.
Yeah.
Reason.
So we're going on a tour. We'll start by establishing the 3 key roles in this ecosystem before we really break down the server's inner workings.
Right.
We're talking its communication layer, the request handlers and capability types, its context stores, session orchestrators, and then finally its caching component.
Great. So to set the stage, we first need to identify the 3 players that are constantly interacting in the MCP architecture. You've got the host, the client, and the server.
Okay, so the host, that's the top layer, right? It's what the end user actually sees and interacts with.
That's it.
So that could be a sophisticated chat assistant fielding support questions, or maybe an AI-enhanced IDE helping a developer write code.
Exactly. And then nested inside that host application, you have the client.
And the client is like the dedicated translator.
That's a great way to put it. It speaks the MCP protocol. It manages the continuous connection to the server. It handles the application side of the whole conversation.
Got it. And finally, we have the star of our show today, the server.
The server. This is a totally separate program, a service dedicated to providing very specific, you could say, atomic capabilities.
So it could be giving secure access to a file system or running database queries.
Or integrating with a web search tool. And crucially, all these different capabilities are exposed through that one single standardized MCP interface.
Let's walk through the interaction cycle because I think that really illustrates the clean separation of labor this system creates.
Good, yeah.
So imagine a user asks the host application, how many new customers signed up today?
Okay.
So step 1, the host, using the LLM, it realizes this isn't a reasoning question, it's a data question. It needs to query the CRM, so it routes the query to the, say, analytics MCP server.
Right. Then step 2, the client, acting for the host, sends the actual request using that standard JSON-RPC message format. The message basically says, hey, run the get daily signups function.
And step 3, the server, which is living right next to the database, it just executes the action, runs the SQL query, gets the raw number, and sends that result back to the client. The AI model itself never even sees the database credentials or the syntax.
And that's key. So for step 4, the client just passes that raw answer, let's say it's 584, back up to the host.
And that's when the LLM takes over again.
Exactly. The LLM takes that number, 584, and formulates the final polished conversational answer for the user. Maybe it adds some context like, that's a 10% increase over yesterday.
The insight here is really that the host and client handle the user interface and the AI reasoning, while the server does all the heavy lifting of action and data retrieval.
It's the ultimate specialization.
Yeah, the AI doesn't need to worry about network latency or specific API endpoints or database connection pools. It just asks the server for the knowledge it needs, almost like that knowledge were local.
Exactly. And, you know, that is a huge leap in building robust, reliable AI applications.
Okay, now that we get the roles, let's zoom in on the server's core, starting with its communication layer. This is the server's literal front door and telephone line.
And the core engine for messages here is JSON-RPC 2.0.
Which is pretty much ideal for this kind of system.
Right. It is. It's lightweight, it's stateless, it's designed for remote procedure calls. So the client can execute methods on the server as if they were just local functions. And using JSON means it's easy to parse and, human readable.
What's fascinating to me, though, is how MCP achieves the context it needs, because JSON-RPC is typically stateless. The crucial first step is this handshake.
And this is much more than just saying hello. When the client connects, the server advertises its protocol version and, most importantly, a list of its supported capabilities.
This is the negotiation phase.
It is. The client learns exactly what resources, what tools, or what prompts the server offers. It ensures both sides agree on the feature set before any real processing starts. This is how the AI knows, for instance, that the server can access the CRM but cannot send emails.
And this is where we get to that paradox of statefulness. The source material notes that even though it's using a stateless protocol like JSON-RPC for the messages, the MCP servers maintain a stateful connection over the session.
Right. They achieve this with an underlying transport layer.
And that's a really critical architectural choice.
It is, because it reconciles two opposing needs, right? You get the lightweight efficiency of stateless RPC for each individual message, but you also get the persistent memory you need for the AI to handle complex, multi-turn tasks.
So they use something like STDIO, which is standard input-output, or an HTTP stream.
Or a WebSocket. But whatever they use, that connection stays open for the session.
Why is maintaining that state so important?
Well, it's absolutely essential for context continuity. If a client asks for page 1 of a massive document, the next request for page 2 can be understood in context by the server.
Without the client having to resend everything.
Exactly. The server just remembers the current position, the task it's in the middle of. It makes the whole interaction so much smoother than if every single request had to start from scratch.
Okay, so the message gets delivered. It moves from that communication layer to the request handlers. Walk us through what these functions are actually doing.
So, request handlers are where the rubber meets the road. They are the functions, the methods that execute the specific actions the server offers. Every single capability advertised back in that handshake is implemented by one of these handlers.
And this is where we really need to nail down the 3 different capability types.
Yes, this distinction is crucial for anyone learning this.
Let's start with resources. What makes something a resource?
Resources are purely for information retrieval. They're passive, read-only endpoints, and they're guaranteed not to cause side effects.
So they're the safest type of interaction.
Absolutely. They're basically providing data access, like a handler that fetches data from a knowledge base or lists the articles in a directory. And for performance with large data sets, these handlers often support things like streaming or pagination.
Then you have tools. These sound more active. The AI gets to, well, act.
That's right. Tools are active operations that let the AI perform calculations or act on the world. They can and often do perform side effects or change state.
So if the AI needs to create a new record in a database or send a Slack message,
or update a user's profile, it has to use a tool. And because these can have real-world consequences, their handlers need much more stringent safety checks, validation, and really clear input-output schemas.
But isn't the line between a resource and a tool sometimes a little blurry? I mean, what if retrieving data causes a log entry side effect? That technically changes the state of the log file. Does that make it a tool?
That's a great question, and it gets to the architectural mindset here. The definition really rests on the intended side effect. If the main purpose is retrieval and any side effect is just administrative, like logging, it generally stays a resource.
Oh, okay.
But if the purpose is to change the business, state like reducing inventory or starting a workflow, then it's definitely a tool. The key is the risk profile. Read only for resources, potential critical change for tools.
Got it. And that brings us to the unique third type, prompts. These aren't about external data or action at all.
Correct. Prompts are reusable prompt templates, or sometimes even sophisticated internal workflows that the server provides to guide the AI's interaction.
So the purpose is consistency and quality control.
Exactly. For instance, a server could offer a SQL query template prompt that helps the AI structure a database query perfectly every single time, including all the required security parameters. It prevents errors and ensures consistency. Even if you swap out the LLM later, the handler just returns a crafted template.
To make that more concrete, let's use that simple example from the protocol docs. A bookmark manager MCP server. It has an add bookmark function. So as that creates a new record, it's categorized as a tool.
Right. And if you use getBookmark to retrieve a bookmark by its index, that's just read-only information.
So it's a resource.
Exactly.
And the third one, suggest bookmark title, which returns a helpful template for creating a catchy title. that is categorized as a prompt. This system really ensures everything has the right scope and security for what the AI is asking to do.
And importantly, during that initial handshake, MCP servers almost always include a built-in handler for capability discovery. That's how the client can ask, what can you do,
Yeah,
and get a definitive list.
that makes perfect sense. Okay, we've given the server the ability to act,
Yeah.
but now we need to look at its internal brain for memory and flow management. Let's shift to the components that give the server its memory, starting with context stores.
Right. The context store is the server's internal storage mechanism. It's used to maintain state between sequential requests, which is vital for any task that spans multiple turns.
And this memory can take a lot of different forms. This is where the architectural choice comes in, right? It could be simple in-memory storage for quick little tasks.
Or standard relational databases like Postgres or MongoDB for more persistent, complex data, or even specialized systems.
Like vector databases.
Exactly, that's a great example. If you're running a resource handler that provides semantic search over a huge knowledge base, the context store behind it might be a vector database. The server integrates that complex tech and just presents it to the AI as a simple, searchable resource.
And the context store can also interface with external services, like Salesforce, to cache relevant data locally.
It can. The main benefit here is supporting context-aware tools. Think of a server built for browser automation. It has to store cookies, open tab IDs, and temporary form data in its context store so it can handle a multi-step request without losing its place.
So if the context store provides the memory, the session orchestrator provides the traffic control.
A good way to think of it.
But if the client is already handling the main session logic, why does the server need its own orchestrator? That feels a bit redundant at first.
It does, but it's necessary because the server often needs to manage these complex, multi-step actions internally that have to be isolated and reliable. The orchestrator's job is to decouple the internal messiness of a multi-step operation from the client's simpler view of the session.
Give us that classic example again.
Find the cheapest flight to Paris.
Right.
That isn't one atomic request. It's a sequence of actions the server's tools have to execute. Step 1, open a browser. Step 2, fill out the form. Step 3, authenticate. Step 4, scroll through pages of results.
And the orchestrator manages that whole sequence reliably.
Precisely. The orchestrator maintains the temporary session data, it links the sequential requests together, and, this is crucial, it handles robust cleanup. If the client disconnects or times out halfway through the search, the orchestrator makes sure that browser instance is closed and the temporary data is cleared.
So you're trading a bit of increased server complexity for a much cleaner, more reliable experience for the client.
You are. It provides much more robustness and recoverability for those complex operations.
Okay, finally, let's talk speed. The caching layer. This must be essential since MCP servers are built to talk to what can be very slow external data sources.
Oh, absolutely. Big enterprise databases, rate-limited public APIs, legacy systems.
Caching is the solution for efficiency, but it's also where the really hard architectural trade-offs live.
It is. The fundamental tension is always between speed and freshness. And we see several strategies mentioned. You have in-memory caching for quick reuse things like stock prices for a few seconds.
Or temporary.
Then there's persistent caching, using something like Redis for data that needs to live across different sessions, and even multi-level caching where you check the fastest memory cache first, then move to slower storage.
And in the most aggressive strategy, prefetching.
Where the server actually predicts what data the client will ask for next and loads it in advance. It's great for document viewing. You're reading page 1, it's already loading page 2 in the background.
But all of this speed, it introduces the classic computer science challenge, invalidation.
That's the million-dollar question. When do you refresh or remove the cached data? For a public stock quote, a 30-second delay is probably fine.
But for a critical patient record in a healthcare app,
Even a 1-second cache delay might be completely unacceptable. It forces developers to implement these aggressive write-through mechanisms to ensure the AI always gets real-time, accurate information. And all that complexity is hidden away inside this layer.
so if we step back and look at the whole picture, the integrated strength of this MCP server architecture is really clear. The communication layer gives you the handshake, and the stateful channel.
The request handlers perform the actual actions, whether they're passive resources, active tools, or guiding prompts.
The context store gives the server its memory, session orchestrators manage the reliable flow, and caching ensures performance across slow systems.
This architecture really captures a critical mental model for how modern LLM applications should be built. It's all focused on maintainability, modularity, composability, and maybe most importantly for any enterprise, control.
That focus on control is so key. The source suggests MCP could become a foundational layer, right alongside standards like Dockerfile or OpenAPI. So what are the practical implications of that kind of standardization for developers?
Well, it means that every distinct sensitive AI capability, from querying a restricted database to initiating a secure transaction, becomes a standardized, auditable, modular microserver.
So organizations can integrate new tech or pivot their app's functionality incredibly quickly just by plugging in a new server.
Exactly. Instead of a huge monolithic application where everything is tangled together. But I think the deeper implication is the granular control this gives back to the developer.
How so?
You control the specific security protocols, the data retrieval logic, and the execution environment of that server, separating it completely from the core AI reasoning engine. This means organizations can achieve regulatory compliance, say GDPR or HIPAA requirements, at the specific server level, instead of trying to audit one gigantic LLM application.
That's a game changer.
It is. That level of verifiable, granular control and auditability is what will define the next generation of robust, enterprise-ready AI software.
So here's the thought I want to leave you with. If every single AI capability becomes one of these standardized modular servers, what does that really imply for how quickly companies can build or pivot their entire business logic? And maybe more importantly, what level of fine-grained control does this finally give back to the developer in a world of increasingly complex AI systems?